(27) CPS Geometry. The Golden Section and the Fibonacci Sequence. Part 2. Recursive sequences are common and accepted all over mathematics. Probably one of the best known is the Fibonacci sequence. Each number in the sequence is the sum of the preceding two numbers in the sequence. Let's note. In classical geometry, the golden section is defined using the ratio between segments. In the same time, the Fibonacci sequence is defined using the addition of two consecutive numbers. The ratio of two consecutive terms tends to approximate very quickly to the golden section by values alternatively greater and smaller than the golden number. The ratio of every other two terms in the Fibonacci sequence tends to approximate very quickly the square of the golden number. This pattern can be extended by taking terms from the Fibonacci sequence further and further apart. These ratios generate all the powers of the golden number. Let's dig deeper into the connection between the golden section of the classical geometry and the Fibonacci sequences of natural numbers. As we will see, the patterns discovered in the close packing of spheres provide a solid foundation and a clear explanation of this undeniable relationship. The existence of the icosahedron pattern in the CPS provides a way of defining a ratio of natural numbers that have a similar geometrical interpretation to the golden number defined in the classical geometry. The third definition of the golden section, introduced in the previous video, can easily be applied to the icosahedron pattern. Using the same approach used in the classical geometry, the icosahedron pattern can also be imagined in CPS geometry as being formed by three mutually orthogonal golden rectangles. Following this approach, the golden number is the limit of the ratio between the longer and shorter side of the three orthogonal rectangles, defining the golden icosahedron's pattern in CPS. For example, the value of the corresponding CPS equivalent of the golden number for this icosahedron pattern can be calculated as the ratio between the numbers of small squares that define the CPS golden rectangle, 26 divided by 16, and is equal with 1.625. These two numbers, 16 and 26, can be used next as the first two terms of a Fibonacci sequence. 16, 26, 42, 68, 110, and so on. Icosahedron patterns, defined by CPS golden rectangles, using higher terms from this Fibonacci sequence, generate CPS ratios that get closer and closer to the value of the golden number, determined using the classical geometry. 1.618033, and so on. In classical geometry, the similarity theorem is used to associate similar triangles, using ratios. The ratios are in fact based on the multiplication. Multiplication is the inverse of the division. The Fibonacci sequences are defined using the addition. The current term in the sequence is equal with the sum of the previous two terms. But, as we have seen, the segments from the classical geometry also obey the addition rule. And, in the same time, higher terms from the Fibonacci sequences obey the multiplication rule. The double properties of both the Fibonacci sequences and of the division of segments into the extreme and mean ratio provide the clear answer to the connection between the discrete geometry described by the CPS geometry and the classical geometry. Can we find other correlations regarding the golden section between the CPS geometry and the classical geometry? The answer to this question is a sound Yes. As we have seen in the previous video, in the classical geometry, the pentagon is born by the golden section and is also impregnated with the golden section. The icosahedron and the dodecahedron are dual. Pentagonal faces are found as bases of the pentagonal pyramids, obtained by cutting the icosahedron with planes under the corresponding angles. The process of constructing a dodecahedron from the icosahedron has also produced the great stelled dodecahedron. This object encapsulates very well the properties and characteristics of both patterns, the icosahedron and the dodecahedron. The diagonals of the pentagons are clearly visible, as the intersection lines between the faces. Observe the great stelled dodecahedron for a while. Nested inside this pattern, one can see a small dodecahedron. The nested sequence of great stelled dodecahedrons and the dodecahedrons can be extended indefinitely, in both directions, toward the very small and toward the very large. This again is an amazing fact. I like to think of this object as being one of the best arguments one can use to justify the validity and necessity of the CPS geometry. The golden section of the pentagon, and the fractal nature of space, is clearly seen in this pattern. The definition of the golden section, based on ratio between the diagonal and the length of a regular pentagon, is closely related to the fact that pentagons can be infinitely nested. Similarly, the 8 faces of the icosahedrons have an underlining hexagonal lattice and define nested triangles. The number of struts needed to construct such nested triangles can be interpreted as being terms of a Fibonacci sequence. For example, one of the sequence shown here is 7, 9, 16, 25, and so on. Again, as stated before, nested triangles, defined by higher terms, from the Fibonacci sequences, can be identified relatively easy in the CPS geometry. Before concluding this video, let's look into the relationship between the golden number and the arithmetic geometric mean, AGM. The arithmetic geometric mean was heavily used by Gauss for computing the elliptical integrals. Since then, the AGM has been employed in developing many numerical algorithms, including the ones used for the calculation of pi. Let's restate a remarkable fact about the golden number powers sequence. The sum of 2 consecutive terms determine the next term. The golden number sequence encapsulates a double property. 1. An additive relationship that can be seen as a modified arithmetic progression. 2. A multiplicative relationship, defined by the fact that the terms form a geometrical progression. In other words, every member of the sequence is the arithmetic mean of the previous and next terms. And also, every term in the sequence is the geometric mean of the previous and next term. So, every term in the sequence is the arithmetic geometric mean of the previous term and next term. One more thing, Gauss refers to the complex domain as being the domain of the arithmetic geometric mean. Let's remember this.